Hey guys, what's up? Welcome to the Physics C, and this is Brian here, and we're gonna solve Unit 6, Problem 12 from the Physics C E&M textbook by John McGeHee. So let's read the problem first. A conducting rod having a mass of 1/10 of a kilogram slides without friction on two conducting rails 50 centimeters apart and inclined at an angle of 10 degrees with the horizontal. A uniform 0.1 Tesla magnetic field acts vertically upward. A battery attached to the rail causes a current to flow up one rail through the rod to the other rail and back to the battery. What must be the current and its direction of flow in the rod that will cause the rod to slide up the incline at a constant speed? Alright, so since this question involves an incline, it might be a little confusing. So first let's draw out our diagram. So let's look at it from up top. So we have the two rails over here and battery over here. There you go, okay. And now the reason I kept this battery as a box is because we're not exactly sure which way our current is going to go. So let's first draw our rod in two. Okay, so let's say this is our rod. Now the question said that the rod is, it conducts. So essentially what this rod does is it completes the circuit for us. So we have two choices for us. We need to decide if our current I is going to go this way or this way. So let's go to our side view and let's take a different, I'll take the same color. And so let's say this is our incline right here. Alright, let's mark it up. So let's say here is our theta, that's 10 degrees, right? And then here is our rod, right over here. Alright. So, and also they're saying that the magnetic field goes up vertically. Now, caution, it doesn't go, the magnetic field doesn't go like this. Instead, the magnetic field is going up in this direction. So that's quite intrusive, alright. So, let me put in an arrow so we know exactly which direction to be at. Alright, so the idea that our goal in this problem is to make the rod go up this way. Alright, but if you know, as you know, the force has to be perpendicular, the magnetic force has to be perpendicular to the magnetic field and the direction of the current. As shown in the equation, Fm equals I L cross E, right? So if that's the case, we gotta use our right hand rule. So let's say our force needs to go into the page, right? That's the way our force wants to go. If that's the case, our magnetic field is going up like this. Alright. So essentially we're taking a front view of this, so we're looking at this straight on like that. That's our view over there. Alright? So if that's the case, if we follow our right hand, so let's draw, hopefully I can draw a good hand. That's good enough. Our thumb, or our velocity, actually no, the direction of the current is pointing this way. Alright. So now we know which way our current needs to go. So let's draw that in. So our current needs to go this way. Awesome, so we solved half of our problem right there. We know which way our current needs to go. Alright, so now we need to find out how large our current is. So let's make this diagram smaller. I'm going to draw a little more on the side view. Alright, so this guy. real quick. So let's mark it up furthermore. So, as I said before, your magnetic force can't be up on a slope like this, alright? So, it has to be perpendicular. And we know our magnetic force wants to go this way, alright? So, how are we going to find this little slope right here? Well, we can make a triangle like this, so this is our theta, and as you can notice, that becomes cosine. As you can tell, this component right here is the cosine theta part of it. So actually, our force is just, it's cosine theta. Alright, but if that's the case, if that's our only force, it's going to accelerate upwards, so we don't need it, right? But yes, we do, because we still have gravity to consider. So we're back to mechanics here. Now remember, in mechanics, this doesn't, as we know, this doesn't mean this, right? So in mechanics, we always made a triangle like this, with this as theta over here, right? And this part must be that little bottom of the triangle right here suggests the direction right here. So this must be mg sine theta. Alright, so now we have our two forces that are involved. So we can go set up our equation. And as we all remember, F equals ma. That's pretty unforgettable. So let's actually go set that up right now. Purple would work. So the sum of our forces, I guess, along the incline, we'll call this x, it's positive, is equal to Fm cosine theta minus mg sine theta. And since our acceleration is 0, because remember, as the question said, we just want the rod to slide up the incline at a constant speed. So that means there's no acceleration and therefore no force. So essentially, these two guys are supposed to balance out. Alright, let's put a big fat 0 right here. Don't worry, that's not your test. Alright, I guarantee if you follow this video, your test will be an extra 0 and an extra 1 in front. Don't worry. But 0 is a good number for this problem because it makes it a lot easier. Alright, so let's rearrange the equation a little. Fm cosine theta is equal to mg sine theta. Alright, and let me make this a little smaller so I can write a bit more. Put this up here. And with that in mind, let's substitute our Fm. Which colors one more time. So if we, as I just said earlier in the video, Fm equals I, L, oh boy, L cross B. Alright, so what exactly is our direction? Well, as we said before, our current is going this way, and our magnetic field is going out of the page, according to this diagram right here. So if that's the case, really what's going on is, let's redraw it again. So this is B right here, and this is, actually let's make it go to the left, because we always think the left right here. Right? This is just the right angle right here, right? So it's sine 90, which as we know equals 1. So we can literally just sub everything in. So instead of Fm, we put I, L, B. Oh, we don't need it. Cosine theta. Remember, these aren't vectors anymore. They're scalar quantities for now. Equals mg sine theta. Alright. So what was the question asking again? It was asking how strong our current needs to be. So the variable we're solving for right here is I. Let's rearrange it one more time. I equal B theta over LV. Alright, so now really all we need to do is plug and chug and celebrate that we're almost done with the problem. Alright, so let's do that here, and I'll do the dirty work. I'm gonna plug everything in. Wish me luck. Alright, I equals 4.1 kilograms. This is the mass of our rod. Alright, multiplied by gravity. So right now we're finding the gravitational force. Alright, and then tangent theta, and we know our incline 10 degrees. And over here on the bottom is part of our magnetic force, and that is L, which is, as you remember in the problem, let's bring it out again. It says 50 centimeters apart. Well, at least the rails are 50 centimeters apart, and that's where the current is flowing through. So that's all we need to worry about. So, and remember, centimeters is not what we need meters, so that's 0.5 meters. Alright, and then we need to find, we need to know our magnetic force, which is not force, the magnetic field, and that is at, give our problem a look again, is at 0.1 Tesla. Okay. Alright, so that's nice and swell, but we need to give our units a check. But that's not gonna work. Oh, cut off. Oh, that's okay. So are you? That's not good. Alright, we'll have to cut it off. That's okay. Fix that up. Alright, let's give that a little fixer up real quick. Alright, so back to where we were before. We need to give our units a check. Alright, so kilogram meters squared, kilograms is meters over second squared, as we all know, gives us units. Tangent 10 degrees just gives us a no units. Alright, let's move on to the bottom. Over meters. And a Tesla is, if I remember, a Newton per amp meter. Alright, that's quite interesting. Meters cancel out. Amps go straight up to the top. Guess what? It's amps at the top. So we're all set to plug. Just put this guy into our calculator. And what we end up with is about let's change our color one more time. About our current is about 3.46 amps. And don't forget, we need to specify our current. So they want it in terms of the rail. So let's say from right rail to left rail. Right? So that is our answer right here. So let's make a quick recap here. So the confusing parts about this problem are that this thing's on an incline, and the fact that it's the conducting rod that completes the circuit. And as I forgot to mention, the magnetic fields over here cancel out, right? And the battery's here, so that doesn't really matter. So all that matters is the force right here. Alright. To do that, we have to know which way our current is going, and then we have to use the right-hand rule to determine. With our right-hand rule, we're able to determine that our current is going in a counterclockwise direction in terms of this picture. Good boy. Well, in terms of this picture right here, it's going counterclockwise, and then Now we know our supposed magnetic force, but that doesn't match up with the incline, and that goes the same with the gravity. So we have to review, go back to our mechanics concepts and split these into components. And then finally we can set up our equations, and we finally solve it. We plug and chug, and we finally get 3.46 amps. So I hope this is a great help for you, and I hope this does give you some clarification, especially with the confusion between the magnetic field and the incline. Remember, it's not going perpendicular to the incline, it's going up by itself. So I hope this is